probability theory mo?
Meron.
Wala ako. Wala ako.
Wala. Ikaw?
Wala din.
Proponent ng probability theory? Wala.
Wala. Probability theory? Wala eh.
According to legend, probability theory began as a branch of mathematics with a correspondence between Blaise Pascal and Pierre de Fermat in 1654. But this is said to be wrong. Years before Pascal and Fermat ever thought of defining the true worth of a chance, isolated problems of a probabilistic nature have been tackled by some of the mathematicians, and one of which is John Grant. It would be better to say that they supplied the vital links of the chain of reasoning that gave us the probability theory as we know it today.
Straightforward counting of population and economic wealth goes back to antiquity. The numbering of people of Israel, Emperors Augustus' balance sheets of Roman Empire, and William the Conqueror's inventor of his possessions, the Doomsday Book, are a few of the most outstanding historical examples of gathering data. The London merchant John Grant, 1620 to 1674, was the first to draw an extensive set of statistical inferences from the massed data. In 1662, Grant produced a tract entitled Natural and Political Observations Made upon the Bills of Mortality, a work that may be said to have launched the discipline we now called mathematical statistics. The researches of Grant include in his book secured him the honor of being one of the charter fellows of the Royal Society of London when it was founded in 1669. With the 119 original fellows, scientists, doctors of medicine, and doctors of divinity, noblemen, lawyers, civil servants, and literary men. Grant was the only shopkeeper. There is a story the sirs were uncertain whether to admit Grant to their number because he was only a tradesman in the city, and they sought the opinion of Charles II on the matter. The king replied that they should certainly admit Mr. Grant, and if they found any other tradesmen, he should be sure to admit them also without delay. As it happened, the society was able to follow this advice while Charles was still alive, and elect another distinguished shopkeeper, a fellow in 1679. Antoine van Leeuwenhoek of Delft was recognized for his pioneer microscopical observations.
The other source to which probability theory owes its birth and development is gambling. But where did the concept of gambling originate?
Gambling originated in the early stages of human history. It was not an invention of a single people, but appeared at many places in the world. It is reasonable to guess that it evolved from some sort of divination rites, most likely divination by lot. Almost every primitive culture engaged in some sort of dice play. The predecessor of the die and most common gambling device of early peoples was a tarsal bow. This is from the hide foot of a hoof animal. Archaeologists digging in prehistoric sites have uncovered many of these hard, solid bones among the debris. The Stragolus, because of its peculiar oblong shape, can rest on only 4 sides, 2 of them broad and 2 are narrow. The 4 sides differ sufficiently in appearance to make it possible to distinguish among them, so that the early straggler are not marked. The 6-sided die may have been obtained from the stragglus by grinding it down until a rough cube was formed. Whether the die evolved in this way or in some other way, it was well known before the birth of Christ. About 1400 BC, the present arrangement of dots with two partitions of 7 imprinted on opposite faces was introduced. One question we shall never clearly resolve is when people first started to play games of chance. In Egypt of 3500 BC, a board game called Hoods and Jackals was played in which counters were moved according to certain rules by throwing the stragali.
According to Herodotus, it started with the legions. The legions' way of adopting from the family was to engage in games one day so entirely as not to feel any craving for food, and the next day to eat and to abstain from games. But according to Cardan, goblins were invented during 10 years siege of Troy to reinforce the mood or the moral of surrounding of the Greek soldiers who suffered from deep boredom.
By the time of the emergence of Rome, gambling with dice was a commonplace recreation, not only among educated classes, but also among the middle and lower classes.
Although gambling was in the great favor of Greeks and Romans, the Jews forbidden it under the penalty of death. The reason for this condemnation is that the gambler always expects to win, and therefore to get something for nothing, and rabbis consider this as immoral and leads to robbery.
The other form of gambling is card playing.
Did you know that the now stylized face cards were originally portrait of an actual person? For instance, there are the 4 emperors, namely David for spades, Charlemagne for clubs, and Alexander the Great for hearts, and Julius Caesar for diamonds. This is a representation of the 4 monarchies, namely Jews, the Franks, the Greeks, and the Romans.
One might assume that during the several thousand years of dice play, preceding, say, the Renaissance, some rudiments of a probability theory would have appeared. Yet, no link between mathematics and gambling was suspected. There is a little evidence to suggest that anyone thought that calculating the frequency of dice falls was possible, or even that each face would turn up with equal probability. Several explanations for a late emergence of probabilistic notions have been offered. Possibly, the dice used were imperfectly in balance, precluding noticeable regularity in their falls, or perhaps absence of a suitable mathematical notation hampered a critical investigation into the laws of chance. A more powerful reason might be that randomness itself was an idea alien to the prevailing modes of thought, not only according to the Christian Church's teachings on absolute truth about accord with far more ancient ideas of divination, God or gods directed earthly events. Whatever the reasons might have been, it is undeniable that a doctrine of chance happenings took a remarkably long time to develop. One of the earliest problems that can be classified as a question in probability theory concerns the fair division of stakes between two players when the game is interrupted before its conclusion. This is first found in print in Farlucas Summa Arithmetica Geometrica Proportioni et Proportionalita in 1494, where among the unusual questions he proposed the following. A team plays ball so that a total of 60 points is required to win the game, and the stakes are 22 ducats. By some incident, they cannot finish the game, and one side has 50 points, and the other is 30. what share of the prize money belongs to each side. Fra Lucas' response to the problem of points is that the stakes should be divided in proportion 5:3, the ratio of the points already scored. Which is wrong. But Cardan said to Fra Lucas' work, "There is an evident error in the determination of shares in the game problem, as even a child should recognize, while he criticizes others and praises his own excellent opinion. Because, as for him, if X and Y are the numbers of points owned by each team, Z is the total number required to win, the stake should be divided in the ratio 1 plus 2 plus 3 ... plus Z minus X is to 1 plus 2 plus 3 ... Z minus Y." Which is wrong. Tartaglia, Cardan's enemy, also commented to Fra Lucas' work. He said, "His rule seems neither agreeable nor good, since if one player has by chance 10 points, would take all the stakes, which obviously does not make sense." For Tartaglia, if Z is the total number of points needed to win, X and Y are the points in hand, then the player with the most points should take a portion of 1/2 plus X minus Y over 2Z of the stakes. Thus, the total stake in Fra Lucas' problem would have been divided into 2:1.
Sadly, another incorrect.
Many years had passed until in 1654, Pascal solved the problem with the correct ratio of 7:1. This may be well considered a decisive breakthrough in the history of probability theory.
Pascal was born in Clermont, France in 1623. Pascal was only 3 when his mother died, and when he was 8, his father moved Pascal and his 2 sisters to Paris. Once in Paris, Pascal was homeschooled by his father, who did not trust the local schools. Pascal's father attempted to steer Pascal, whom he recognized as a prodigy, toward literature and language, forbidding Pascal from studying mathematics and geometry. As an amateur mathematician himself, Pascal's father feared an interest in math would cause his son to forego learning other topics. However, the decree only piqued the young genius's interest, and before long Pascal was teaching himself geometry. After discovering this, Pascal's father relented, teaching his son Euclid and allowing the young Pascal to accompany him to meetings of the local mathematical society. There Pascal met and conversed with many of the leading mathematicians of the period, including Marie Mersenne and Pierre Gassendi. Before long, Pascal was ready to publish his own findings. In 1640, he published the Essay on Conic Sections, which made important advances in the transcription of objects onto 2-dimensional paper. Pascal showed his father's fears to be unfounded, as Pascal soon found other meaningful pursuits in addition to theoretical math. In 1642, he created a rudimentary calculator to aid his father in tax calculations. In the mid-1640s, Pascal also took up an avid interest in physics, and his 1651 Treatise on the Vacuum turned contemporary attitudes concerning the existence of vacuums on their head. In 1646, Pascal experienced a profound religious awakening. When his father broke his hip, 2 bone setters who were also Jansenist converts stayed with and cared for Pascal's father. Pascal soon realized many Jansenist beliefs were closely aligned with his own personal faith, and he became a devoted convert. In the 1650s, in part due to this religious conversion, Pascal's writing became increasingly philosophical and driven by his religious beliefs. In his 1656 Provincial Letters, for instance, Pascal fiercely defended the teachings and beliefs of the Jansenists against contemporary attacks leveled at the Catholic sect by Jesuit priests. Pascal died in 1662, only 39 years old, after an undiagnosed illness which historians surmise may have been a stomach tumor. The Pascaline, as he dubbed the calculator already discussed, was only marginally successful, though it did have its intended effect of making his father's job easier. Many of Pascal's greatest accomplishments were in mathematical theory or in physics. For example, when Pascal took interest in physics, he single-handedly changed the prevailing theories on vacuums. Prior to Pascal, most early scientists believed vacuums of space to be virtually non-existent, trusting in the ages-old Aristotelian maxim that nature abhors a vacuum. However, Pascal disproved this theory by using a recently created device devised by Evangelista Torricelli. Torricelli essentially created the first atmospheric pressure barometer by taking a tube of mercury and placing it upside down in a bowl full of mercury. Pascal caused a sensation when he successfully demonstrated in his treatise on the vacuum that the space which emerged at the top of the tube when the air pressure forced the liquid into the bowl was indeed a vacuum. The achievement Pascal is perhaps most known for is pioneering mathematical probability theory in concert with his colleague Pierre de Fermat. The two exchanged letters discussing thought problems and experiments they both conducted using dice and other seemingly chance outcomes. Through their correspondence, Pascal realized that the outcome of any roll of 2 dice was not as random as it seemed. Indeed, each outcome instead had a fixed probability. For example, rolling 2 dice can come up 7 several different ways: 3 and 4, 1 and 6, or 2 and 5. However, rolling a 2 can only occur once, when both die come up as 1. Finally, Pascal was an accomplished philosopher in addition to his work in math and physics, specifically after his Jansenist conversion. He defended his own personal religious beliefs and those of the Jansenists in several publications in the 1650s. Pascal believed that only through submission to God can man gain true knowledge. Scientific and mathematical work, including his own, could provide explanations of the natural world, but could not claim to be universal. Pascal further combined his fervent belief in God and his work on probability theory to show that it is reasonable and prudent to believe in God. According to Pascal, God's existence has only 2 outcomes: either he does or he does not. If he does not, our choice to believe or not believe has no impact upon our current lives. However, Pascal argued, if he does exist, then our choice has an enormous effect, leading to either eternal happiness or eternal damnation. Considering the number and scope of Pascal's achievements, it is truly unfortunate the Frenchman never saw his 40th birthday. In his short time, Pascal achieved much, becoming an accomplished and published mathematician before the age of 16. He went on to prove that vacuums existed in the universe after becoming interested in physics. After having a significant religious experience, Pascal became a Jansenist and spent the remaining decade of his life defending Jansenist beliefs. He also pioneered probability theory in this decade and used it to argue that it is reasonable to believe in God.